let's look at how to use Faraday's law and learn what we can about the properties of this new kind of induced electric field that appears in the presence of a changing magnetic flux. So in a quick recap, we had modified Kirchhoff's law around a closed loop by adding in this new term, this Faraday term, and noting that if we move around a closed loop and return back to where we started, then the delta V along that whole path is 0, V final equals V initial, so that these two terms can be set equal to each other, and that's what we're calling Faraday's law. And what we're saying here, in words, what this equation means is that the integral of EDS around a closed loop, that's a closed path integral, is equal to the opposite of the rate of change of the magnetic flux, defined thusly, the magnetic flux, through the open surface bounded by the closed loop indicated here. So that's an open surface integral to find that flux. And what we're going to do is apply Faraday's law here to a specific example scenario. So consider a solenoid here with a current coming in this direction, looping many, many times around that coil, and current coming out there. Let's let this little current be a function of time. So this time-dependent current, little I of t, will be generating a uniform magnetic field inside this cylindrical solenoid of radius r and turn density little n, according to what we've called the Bunny equation. So we see that the magnetic field strength inside the coil is directly proportional to the current running through that coil. So if our current varies with time, then the B field strength in here will be varying with time. So in this way, by controlling I, we can sort of adjust the B field on the inside, increasing it or decreasing it in strength with time, producing a time-dependent magnetic flux through any loops we should draw inside the coil here. So that's how we're actually going to achieve a time-varying magnetic field. Our goal then will be to determine the electric field throughout this whole region, both inside the solenoid at radii distances from the axis of the solenoid r less than big R, and also outside of the whole solenoid at distances from the axis little r greater than big R. Here are the steps for how to use Faraday's law to do so. Okay, so this is a view down the mouth of the solenoid. We've got this orange copper wire here looping many, many times, and suppose our current is running counterclockwise through that loop, generating a B field pointing out of the page here. So that's according to right-hand rule. Our current looping this way through the solenoid generates a B field pointing with my thumb out of the page. All right, so this current is generating this B field. So far, there is nothing being induced right now. This is not an induced current. This is sort of our starting current that's generating this B field in the first place. Okay, we would like to find the induced electric field that's going to make an appearance inside this region. Step one, draw what we'll call a Faradayan loop located at locations where we want to find the E field. So let's draw a circular loop of radius little r, coaxial with the solenoid. This will be our Faradayan loop. It's a closed path, and we're going to use it to try and find the E field at locations on that path. Choose ds and dA to agree. So we're going to choose a direction to integrate around this path, and then have to choose a front side for the bounded open surface based on right-hand rule. I would like my dA to point in the direction of the B field, so it's parallel to the B field. So if I want dAs that point out of the board, I can achieve that according to right-hand rule, I can get dA's pointing out of the board, so my thumb pointing out of the board, if my dS's go with the curl of my fingers, if my dS's go counterclockwise around that loop. So I'm going to have steps ds, infinitesimal displacements, pointing counterclockwise around that loop. And there I've taken care to choose my dS's and my dA's to agree according to right-hand rule. dS's go counterclockwise, dA with my thumb out of the page. Okay, now that we have a front side for that loop, the side facing us, we can compute the magnetic flux through that loop. So our magnetic flux, phi sub b, which we're expecting to be a function of time, can be found by doing the open surface integral magnetic field dotted with all those dA's across the surface of our surface bounded by this closed path. If B is uniform at all points on that surface and B is also parallel, that is out of the page, it is parallel to dA, then B and dA are in the same direction, and we just get from our dot product the magnitude of B times dA, and then add those up over all little patches of surface for our open surface here. B will be uniform across that, so we can pull B out, and then just add up all the dA's, which will get us the total area of the surface bounded by our closed loop. So our flux as a function of time will be equal to the magnetic field strength, which we're expecting to be a function of time based on the Bunny equation up here, times the surface area of the open surface bounded by our closed loop, which will be just the area of that circle of radius little r, so pi times little r squared. That's the time-dependent magnetic flux through our surface bounded by this closed Faradian loop drawn in red. Okay, that was step 2. We've now got the flux through that surface as a function of time. Okay, step 3. Step 3 here, I want to compute the time rate of change of that magnetic flux, d phi dt. So d phi dt will be equal to the time derivative of this expression here. And if our loop stays the same size, if we're not varying the size of our Faradian loop, then pi little r squared stays constant. And we just have pi little r squared, and we need the time rate of change of the magnitude of the magnetic field inside the solenoid. We could here apply our Bunny equation and note that the time derivative of the magnetic field will just depend on the time derivative of the current. So we could also go on to write this as pi little r squared, the area bounded by our Faradian loop, times mu naught times n, the turn density, times di dt, the time derivative of our time variable current. So as our current changes with time, we're going to get a changing flux here. Okay, next step is to apply Faraday's law. Here's where we're going to think about this induced electric field that we've got. But let me pause for a moment before we go on to evaluate Faraday's law. Let me just ask, what about good old Gauss's law here? That's what we've used in the past to determine electric fields in regions that have a high degree of symmetry, like this solenoidal system. So couldn't we just be using Gauss's law here to find the E field? Well, let's try it out. If we drop a Gaussian cylinder coaxial with our solenoid in this region, so a Gaussian cylinder of radius little r, sort of inside our bigger solenoid here. Here's the end-on view. So this now is not our Faradayan loop, but instead the edge of our Gaussian cylinder, and then apply Gauss's law to that, we note that our solenoid is empty on the inside, so no charge enclosed. That's 0. So there must be no electric flux, no net electric flux through our Gaussian cylinder. Our dA vectors around the wrapper, dA vectors pointing radially outwards, so E dot dA gives us just the radial component of E field, if there is any. And since we know that this equals 0, and the dAs are definitely not 0, we're forced to conclude here that the electric field inside our solenoid must have no radial component. Since there's no charge enclosed, there's no radial component to our electric field. Here's just a reminder, since we have so many different kinds of integrals going on right now. This, in Gauss's law, this here was a closed surface integral. All right, so Gauss's law tells us this, but it tells us nothing about the tangential component of the electric field. So Gauss's law only tells us about part of the field. It doesn't tell us the whole story. Since this dot product here eliminates information about components of the electric field that might be at a right angle to our little dA vectors, we don't learn anything about components of the E field that might be at a right angle to the dA vectors. In particular, we don't learn anything about components of the E field that might be parallel to the dS's along our Faradayan loop, which has the exact same shape as the edge of our Gaussian cylinder here. So Gauss's law is still true and it still applies, no modification of it needed, but it doesn't tell us everything we would want to know about that electric field. So we do need our new Faraday's law here. Okay, on to step 4. Okay, we're going to apply Faraday's law. Here's the statement of it, so state Faraday's law. And let's have a look at the left-hand side and the right-hand side. The right-hand side we've basically worked out already in steps 1, 2, and 3. We just need the opposite of this expression here. So the opposite of this is going to go in there for the right-hand side. Let's look at the left-hand side. E dot ds around this path right here. Okay, so to figure out our directions and signs, our signs and directions here, we're going to need to use our knowledge of Lenz's law. So we are going to have to know what is changing about the magnetic field in this region. So example, suppose we know that the current running through the coil is increasing over time. Someone's turning a dial somewhere that's cranking up that current. So I is increasing over time. And if I is increasing over time, then the magnetic field strength inside the coil is increasing over time. So our magnetic flux is increasing over time. So if I is increasing, we're getting more magnetic flux out of the page. So our positive magnetic flux that we solved for right here is increasing with time. So d phi dt is greater than 0. We're getting increasing flux out of the page. Now, Lenz's law tells us that the system is going to respond to that. There's an inertia in the system that's going to try and keep the magnetic flux what it was. So our induced E field is going to appear in an attempt to oppose this changing magnetic flux. We're going to get an induced E field that tries to put magnetic field back into the page. Since we've got increasing flux out of the page, our induced E field will appear to try and put magnetic flux back into the page, opposing that change. So what kind of E field would accomplish that? Let's see. Based on our knowledge of electromagnets here and the magnetic fields that they generate, we can see that if inside the solenoid here, if say there was like a wire sort of a wire loop located where this Faradayan loop is, and there was able to be current running through that loop, then if a current ran clockwise around this loop here. If there was a wire here, and if current was able to run through that wire clockwise, then that current would be, according to the right-hand rule here, that current would be generating B field into the page. A clockwise current running around here would generate B field into the page, which is exactly what we need to counter the increasing magnetic flux out of the page that this current is generating. So what we might have, so if there was a wire here, we would get an induced electric current running clockwise by Lenz's law to add B field into the page. Now, there is no wire here, but our induced electric field is going to show up anyway. We're going to get an induced electric field along this path, trying to drive a clockwise current, attempting to maintain the flux, even if there are no actual charges here to push. Even if the space is empty here, an induced E field will appear in this space, pointing clockwise, trying to push charges, trying to oppose the change in flux. Now, we already know from Gauss's law that any E field inside here has no radial component, so it must be only tangential. And we've concluded that the E field must be, our induced E field must be pointing clockwise at all locations around this loop, trying to drive an induced current clockwise to generate a magnetic flux into the page, opposing the increasing flux out of the page. So that's what we've just done here. Based on our knowledge of Lenz's law and our knowledge of how the flux is changing, we've determined that the induced E field, what I've drawn here in green, the induced E field must be anti-parallel to ds at all these points. That's what we needed to know in order to evaluate the left-hand side of Faraday's law right here. So E and ds are anti-parallel to each other, so when we dot them together, we get a minus sign, so minus the closed path integral of the magnitude of this induced E field times ds equals, and on the left-hand side here, we have the opposite of the time rate of change of the flux, so the opposite of this expression, pi r squared, and I'll leave this as the time rate of change, ddt, of the magnetic field strength inside the coil. All right. Having been careful about our signs, we'll see that these two negatives will cancel each other out. Noting also from symmetry that the E field strength must be the same at all points on this loop from our cylindrical symmetry here. So E is the same strength for all ds's, so we can pull out E, and we're left with the closed path integral of all those little steps ds equals minus pi r squared. Our minuses have canceled out. dB dt. Adding up all those ds's just gets us, adding up all these ds's just gets us the circumference of our Faradian loop of radius little r. So E times 2 pi little r, the circumference of a Faradian loop, equals this expression over here. And we can conclude that our electric field strength as a function of little r, and potentially as a function of time, since the right-hand side is a function of time, our E field strength as a function of distance from the center of the solenoid and time equals this divided by 2 pi r. So we'll have 1/2, the pi's will cancel, r times the time derivative of the magnetic field strength inside that region. And what we've discovered here is that we're going to get an E field strength that is directly proportional to the distance from the center of that solenoid. An induced E field. This is our induced E field here, this interesting new kind of field that depends linearly on R. So it gets stronger as we go towards the edge, the inner edge of our solenoid. So it's 0 at the center, no E field at the center, and then gets stronger as we go further out. So here I've drawn our electric field lines, and we know the spacing between the lines indicates field strength. So our lines are more closely spaced near the edge, where this says our E field gets stronger. But note also the shape of them. We worked out here from the geometry and our symmetry considerations that our E field must be tangent to one of these Faradayan loops everywhere, which means if we connect up these E field vectors, they will form a circular loop. And these, in green, are not magnetic field loops. These are electric field loops. We have looping electric field lines that do not begin or end on electric charges. This is a very different electric field from anything we've ever seen. These electric field lines look more like magnetic field lines, like these closed loops with no beginning or end, but they are most definitely electric field. So this is one of the very unusual and different properties that these induced electric fields have that electric fields produced by charges do not.